Hello everyone. Today we are going to talk about power quality of the system. When we talk about power quality, first we think about what is from the power quality. Power quality is the degree to which the electrical supply remains within the acceptable voltage, frequency, and waveform limits. A high quality supply allows equipment to operate reliably, efficiently, and safely. Power quality problems may originate from the utility, the installation, or customer loads. Then we talk about why power quality matters. In there, we, we can go step by step. Mm, Unexpected equipment trips and interruption. Reduce motor and transformer life. Overheating of cable, transformers and neutral conductor, data loss and malfunction of electronic equipment, increased losses, lower power factor and higher operating costs, production downtime and maintenance costs. These are the main power quality parameters: voltage magnitude and voltage variance, frequency, voltage waveform and harmonic distortion, voltage unbalance, voltage dips, swells and interruptions, transient and electrical noise, power factor and reactive power. Let's talk about voltage sag or dip. So in that case, short duration reduction in RMS voltage, commonly caused by faults or large motor starting or large load, typically affects contactor dropout, PLC resets, drive tripping, and lighting flicker. For the mitigation this issue, we should use for the large motor soft starter or PFD, also dynamic voltage restorers, UPS system and stronger power supply capacity. Then we talk about voltage swell. So swell means short duration increase in the RMS voltage. Causes including fault clearing, sudden load rejection, and some switching events. From this, we could affect stress on power supplies, light, and sensitive electronic equipment. For mitigating this issue, we should use surge protectors, voltage regulation, UPS, and appropriate control of switching. Then we talk about interruption, temporary or sustained loss of supply voltage. This caused by network fault, production operation, equipment failure, and further maintenance. Uh, for this scenario, uh, we can use mitigation plans as critical facilities may require UPS and standby generators, automatic transfer system, and redundancy. Redundancy means each backup unit should have duty and standby supply. Transient and surges. Very fast change in voltage or current means the transient. Main source of this is lightning, capacitor switching, and inductive loading switching. This can damage insulation, electronic components, and communication interfaces. For this transient and surges, we use speedy bonding, thin and correct coordination of protective device for the protection. This is a important one. Harmonics. Harmonics are waveform component at integer multiples of the fundamental factors, namely third harmonic, fifth harmonic, seventh harmonic, ninth harmonic, like that. Common source is VFD, UPS, rectifier, switch mode, power supply, LED drivers, and EV chargers. This effect transformer heating, neutral overheating, noise tripping, losses, and communication interference. For the solution for this, we have to use passive active harmonic filters, low harmonic drivers, and the suitable transformer and neutral design. Then voltage and current waveforms. When we talk about this, ideal AC voltage is sinusoidal. Nonlinear loads go non-sinusoidal current even when the supply voltage is nearly sinusoidal. Current distortion can create voltage distortion through the system impedance. Power quality assessment should be consider both voltage and current. Voltage unbalance. Three-phase system should have balanced phase voltage and currents. This unbalance happens because of unequal single-phase loading, loose connection, unequal impedance, and supply problem. This effect for negative sequence current, motor heating, vibration, reduced motor efficiency. To mitigate this, we use redistribute single phase loads and correct connection impedance problem. Flickering. Repeated voltage fluctuation can cause visible change in lamp brightness. Typical sources are furnaces, welders, large motor, and rapidly varying load. From this, lighting discomfort and possible process disturbance can be happen. Strong supply, dedicated feeders, reactive power compensation, and load control can be do as a mitigation. Power factor. Power factor indicates how efficiently apparent power is converted into useful active power. Low power factor increase current for the same kilowatt load. Higher current increases losses and voltage drop. Correction method include capacitor bank, active PFC, and properly controlled converters. To avoid overcorrection and consider harmonic resonance when applying capacitors. Power quality in motors and transformers. Voltage unbalance can cause significant motor heating. Low voltage increase motor current for a given mechanical load. Harmonic increase transformer and motor losses. Frequent dips can cause contactor and driver to trip. Correct sizing, ventilation protection, and monitoring improvement reliability. Measurement and monitoring. Use a Class C power quality analyzer where standards-based assessment is required. Measure RMS voltage, current, frequency, THD, individual harmonics, unbalance, dips, swells, interruption. Record events with time stamps and waveform captures. Measure at the point of common coupling and sensitive load when troubleshooting. Common mitigation equipment: surge protective device, UP system, voltage regulators, active passive harmonic filters, automatic power factor correction panel, line reactors and DC choke for drivers, isolation conditioning transformers where appropriate, dynamic voltage restorers and active power conditioners. Power quality troubleshooting approaches. Can talk about step by step. First, identify the symptoms: trip, overheating, flicker, reset or equipment damage. Record the time, operating condition, and affected equipment. Measure voltage, current, and waveform quality. Compare event with switching, motor starting, and process changes. Locate the source, utility, distribution system, or load. Apply mitigation and verify the result with follow-up measurement. As an example, typical industrial power quality problems. PFDs cause harmonic current distortion. Large motors cause voltage dips during starting. Unequal single-phase load cause unbalance. Capacitor banks interacting with system harmonics. Lighting and switching cause transient event. Poor connections cause heating and intermittent voltage problem. Design and maintenance best practices. Perform load flow, short circuit and harmonic studies for complex installation. Separate sensitive load from heavy fluctuating nonlinear load where practicable. Maintain low impedance protective bonding and a robust earthing system. Use correctly rated and coordinated SPDs. Thermographically inspect connection and monitoring critical feeders. Train power quality data instead of relying on one-time measurements. Key takeaways from this discussion: power quality affects safety, reliability, efficiency, and the equipment life. The major disturbance are sexual interruption, transient harmony, unbalance, and flicker. Correct diagnosis requirement, measurements, and event correlations. Mitigation should address the root cause, not the symptoms. Good electrical design, protection, earthing maintenance, and monitoring prevent many power quality problems. Thank you. Please subscribe.